Okay, let's get started. It's 8:30. Okay, let's resume here. I was describing the case 3, a pole and its frequency response. So this is the standard technique for drawing the system with a single pole, to draw its Bode plot. First, check the frequency, the break frequency. Go and find it on the diagram. For example, in this example that you have, I chose omega O somewhere between 1 and the 10, maybe a midpoint here. Call it omega O. If it is in the middle, I tell you what, half unit of scale between 1 and the 10, let's say 0.47. 0.47 is 3. So omega O is like 3 radian per second. Same location in the next scale, it will be 10 times the omega O, 30 radian. And the next one will be 300 radian. So this is how it goes. Here, in the lower scale, it will be omega O over 10. So first mark that point from what you see. Next thing is draw a horizontal line. Let me see if I can find a red marker. I realize I'm running out of markers now. Oh, here. There's plenty. So we mark this point, omega O. Now, to construct the Bode plot, draw a horizontal line. What's the significance of that line? It says if omega happens to be less than omega O, see, it's less than omega O, that number will be much, much less than 1. It's from equations. Omega is, say, a tenth of that. It will be small in comparison to 1. Therefore, under the radical, you have 1. Therefore, the magnitude is 1. Log of 1 is 0. 0 times 20 is 0. That's why it is leveling with the 0 dB. That is why we have to have it in the normalized form. Next, from this point onward, draw a line, draw a straight line with a slope of minus 20 dB per decade. Minus 20 dB per decade. So if this is omega O, the 10 omega O should be here. 10 omega O will be found there. If this is minus 20, okay, so 10 times of omega O, we found it, minus 20. Now, from this point to that point, draw another broken line. Okay, that's it. These two lines, broken lines, are linear approximation to the function itself. So the function is going to go, of course, smoothly, tangential to that line, and then it's going to go down and then become tangential to this slope. And as soon as omega exceeds omega O, you can't even tell it will be a straight line in the graph paper. So the lines convert, curves or functions and curves convert into line segments. However, if you want to know exactly how the function looks like or which points it is going through, there is one advantage at this point. It's correction. It's called correction. The true curve is going to pass minus 3 dB below the omega O. So where is that coming from? It's coming by checking the function. Simply substitute omega equal to omega O here, omega equal to omega O. Then you will notice that the h of j omega at omega equal to omega O will be equal to 1 over radical 2. 1 over radical. So 20 logarithm of 1 radical 2. 1 over radical 2 will be minus 3 dB. So right there, we know we're going to have a minus 3 dB crossing point or passing point. Then what will be the function, the smooth function, not its linear approximation profile, but the function itself. In case if you're interested, which rarely we will be in the designs, you can fit a curve. You can fit a curve that will be asymptotic. Then it will pass through this point. Then it will become asymptotic to that line. The full line will be a better presentation of the function. However, as I said, when it comes to the construction, complete boat construction, you don't pay attention to the curves, but rather you will go with straight line approximation. It will make it much, much easier. So from this point onwards, the slope will be always equal to minus 20 dB per decade. That is a standard. A single pole always produces, for frequencies way above the omega, it will always have a rate of minus 20 dB per decade. You can check it, by taking the difference between omega equal to, let's say, 10 omega and then changing it to 100 omega. Look at the difference that will happen. You will see that it will go down 20 dB. So this will be our dB. But how do you construct that slope? It's very easy. See, once you find this point and you want to construct the line versus the minus 20, because you know omega O, once you find this point, get 10 times of that over here, and then drop it, and then versus the minus 40, level it with minus 40, and then you get 2 points, and then straight away we'll draw the line. Or you can send out the line right from here. Omega O, 0. 10 omega O should be minus 20 dB. Draw a straight line, and you can construct the linear approximation very quickly. That is the whole idea of learning the both plots. Now the phase angle. This one is presentation of another function. Let's go like this. This is our omega. That's 0.1. This is our ones. That is our tens. That's our hundreds. Okay, and so on. So I want to plot theta. Theta is this angle. The inverse tan function. How can we plot inverse tan function utilizing straight line approximation? So this is the technique. Number one, here Omega O is your breakpoint, which is known, comes with the pole. At omega equal to omega O, that is when the frequency, applied frequency, is matching the cutoff frequency, this ratio will be 1. Inverse tan of 1 is 45 degrees. With a minus, it will be minus 45. So we know that here, exactly, here, at omega O, our angle is going to be minus 45 degrees. Then, once you find this point, you establish that point, go find a spot, a point in this location, which is omega O over 10 times lower than omega O. So if omega O was, for example, 3, go find 0.3, which is in this interval. Fix this point. Next, go and find 10 times of omega O, which is here. And level that against the here, against minus 90 degrees. Make that spot. So we got 3 points. And these 3 points will be collinear. Then construct the function, inverse tan function. Dotted line up to here. Straight line up to here, and another straight line going inverse that way. So this is the presentation of inverse tan of x. Inverse tan of x, if you recall, it would be a function that goes like this. Inverse tan of x. X being that way, that's the inverse tan. Of course, since it is negative, it is, of course, the 90 degrees. Okay, now let us make a correction. First of all, we know that this is a smooth function. Kind of, it's not broken and sharp. It's a smooth function. But we know certainly it's passing this point. We are 100% sure it is passing through that point. Why? As I said, if omega is omega O, this is the inverse tan of 1, that's a 45, dead short. Why we are claiming it's 0 degrees at omega over 10? Okay, check it. If you substitute omega equal to omega over 10, this point will be inverse tan of 0.1. Inverse tan of 0.1. That is about 4.8 degrees. So 4.8. 4.8 is only 10% of 45, even smaller. So it's a small angle. So we are approximating the like 4.8 degrees, almost like 0. That's why we're marking that one. Next, why we're calling 10 omega O as 90 degrees? Check it. Put omega equal to 10 omega, you get inverse tan of 10. Put it into calculator, inverse tan of 10 will be close to 85 degrees. So it will be slightly over higher than that spot. That spot is a minus 90. It will be slightly higher. So the designers, when they want to create that smooth curve, the way that we did for the phase angle, if necessary only, we can modify by the corrections that we know how much they are. From this end, we need to go down 4.8 degrees. From that end, we need to go up by 4.8 degrees approximately, roughly speaking. Now we have a pretty good idea how the function is going to look like. The the solid function, the smooth curve of the angle versus the variation of omega, is going to be tangential here, passing through here, passing through that point, passing through here, and asymptotically approaching there. So the blue solid curve is kind of a approximation, kind of refinement of the broken lines. But I tell you what, in the design, we always use the broken lines, not the smooth one. But we are aware. We are aware what happens at the break frequencies at this 10 times higher than the break and 10 times lower than the break. We know that the correction factor is only by about 4.8 degrees. So remember how we got the 4.8. You simply substitute 0.1 omega here, and inverse tan of 0.1 turns to be minus 4.8 degrees. And you substitute 10 omega there, and the angle turns to be about minus 85 degrees, which is that short of 90. So the red is the approximation to the smooth curve. Okay, so I explained how you will project a pole, a single pole, real pole, in the frequency plane as a Bode plot, presented as a decibel against the angle. So the magnitude is easy to construct. Two lines. Get the omega O on the 0 dB, draw horizontal, draw a slope of minus 20 dB per decade. How do you determine the slope? Very easy. If you know omega, you know 10 times of it. Then minus 20, go select minus 20, go and move and find this point. So you have that point, you have this quarter point, draw the line, and that's your minus 20 dB. Here, how do you construct that? Here is how you do it. At omega O, we know it is a 45 degrees because the function is the obvious. It's there, inverse tan of 1. So this is the obvious. 10 times lower than that is nearly 0 degrees. 10 times over that is nearly 90 degrees. So below the 10th, it's 0. Above the 10 times, it's 90. So draw these lines, and the 3 points will be collinear. Draw these, and you have the phase response of the circle. And then if you need, you will go and make a correction. For the angles, you will correct the corners by 4.8 degrees down, 4.8 degrees up. This is a exact passage point, 45. For the gain, you will correct at the break frequency. That's why they call omega O break frequency. You will correct it down by 3 dB. So this spot is truly 3 dB under the break point, just slightly under the 0 line. And then you will construct the Bode plot of single pole. Okay, so that was our case number 3. Now, case number 4, which is a 0. I'm going to construct that for you. Here is how we will do case number 4. And then we will study an example, a combination example. Case 4, 1 real 0. So the transfer function, which we need to get the body of that, will look like S plus omega O over omega O in its normalized form. Okay, so we have to extract the actual transfer function out of it. The actual transfer function will be h of j omega equal to j omega plus omega O over omega O. Magnitude of h of j omega here will be equal to radical, again, 1 plus omega over omega O squared. This will be the accurate function of your transfer function. The angle will be angle of h of j omega, which we call the theta, will be tan to the minus 1 of omega over omega O. So simply substitute j omega here. That's the real part, that's the imaginary part. So the angle will be inverse tan of omega divided by omega O. Now we need to project them on a graph, but in terms of the boat, which is like 20 log of that magnitude. So we will construct the axis omega, and this is the 20 log of h of j omega magnitude in decimal. Okay, so here is how to construct, and of course, let's label the axis. Let's say this is 0.1. Those are my ones, of tens, the hundreds, and the thousands. 1K of radian per second. Okay, first. Look at the break frequency. This is the break frequency. Where is the zero? The zero is at minus omega O. So if you put it in the S plane, j omega and the sigma is going to be here. Minus omega. That's the position of the zero. Zero of a function is a value of S that will make the function equal to zero. Of course, if you substitute S equal to minus omega O, that vanishes. That's the definition. So, once you got the omega O, you will find it, the value on the frequency axis. Let's say omega O is here. So, mark that spot. Now, draw a horizontal line. This means for all frequencies below the omega O, the gain is 0 dB. Let us check that back. This is the gain. If omega is much, much less than omega O, like 10 times less, you're here, let's say. 10 times less than omega O. This will be 0.1 squared. 0.1 squared is 0.01. So under the radical, you will get 1.01. 20 logarithm of square root of 1.01 is approximately just 0. So that's why it's. Now, let us take the omega equal to 10 times of omega O. If omega is 10-fold higher than omega O, under the radical, this will be 10 squared, like 100. 101 is 101. Square root of 101 is almost 10. It's like square root of 100. So you get 10. 20 log of 10 will be 20 dB, because log of 10 is 1. 20. That's it. So you will go find the next spot. Okay. Then you will find the 20 dB on the calibrated axis. Then you will find that spot. The line that joins the two together has a slope of positive 20 dB per every decade, which is this line. Slope will be equal to positive 20 dB per decade. If you go 100 times omega O here, in this spot, 100 times, this will be 100 over 100 square. 100 square plus 1 square rooted will be just 100. Log of 100 is 2. 2 times 20 will be 40. So the 10 times of that frequency is going to coincide with the 40, up there, 40. But we don't need it. We just need the first one, breakpoint, and the next decade, 10. So this is the decade, 10 times of that breakpoint. Once you get the 2 points, you will draw the line. There you have your straight line approximation to this function. Now, correction. How do you correct the smooth curve? There is one point of that curve that we are sure it's going to pass. And that is the value of omega O. Check here. If you make omega equal to omega O, this will be 1. So under the radical, you will get radical 2. 20 log of radical 2 is just 3 dB. That's it. So we know that at the breakpoint, if you go up by only 3 dB, you will get a corrective point right there, which you can place your smooth curve. So your smooth curve is going to be tangential here. It will pass through that point, and tangentially, it will go up. There it is. So that is the correction. This is the corrective point. It may be applied if you want to refine your overall characteristic. But as I said, initially when you're drafting it, it doesn't need refinement. You just go by straight line approximation, which will make the business of addition quite easy. Okay, so we got the function plotted. That was the magnet. Now check this one out. How do we plot the phase angle? Okay, let's see what tools we have. You will construct your linear logarithmic scale. Omega versus the logs of frequencies, 0.1, ones, tens, 100, and 1K radians per second. And this is our angle, 0 degrees, 45 degrees, 90 degrees, then 135, etc., etc. Just keep going. Completely a linear choice for the phase angle. So angle in degrees. This is your theta. Now creating a linear approximation to this inverse tan function. So how do we create 3 lines making up the shape of that inverse tan? You see the method. Number 1, we know that at omega equal to omega O, check, theta will be tan to the minus 1 of omega O over omega O, which is 10 to the minus 1 of 1 equal to 45 degrees. So once you find your omega O here, once you mark that spot from the break frequency that you can see in the first place, create a point here. 45, it's this 45 against the omega O, which is determined from the beginning. It comes with the function. So this spot is found. That's step number 1. Get that point. Then go a tenth down a tenth of this frequency. So 1/10 of omega O is going to be symmetrically here, omega O over 10, in the lower scale of 0.11, 1 to 10, 10 to 100. So they go up in decades, they divide in decades. So find that point. Level it with the 0 degrees. Now, why we are spotting that point as a 0 degrees? Here is the reason. If you make omega equal to 10 to the minus 1 of 0.1 omega O over omega O, and you put that into your calculator, omega O's cancel, and 10 to the minus 1 of 0.1 is about 4.5 degrees. That's what your calculator will tell you. 4.5 degrees is approximated to a 0. That's why it is marked on the 0 degrees. So this is just an approximation. The curve does not pass through that point. It's 4.5 degrees higher, which is like 10% relative to that level. So kind of 10% higher, small. But we will mark this one. Next thing is go find 10 times of that frequency. It's here. 10 times of omega O. Now, if you substitute for the omega, 10 omega O, the value of the function will be, for 10 omega O, will be 10 to the minus 1 of 10, which will be 85 degrees. Not quite 90 degrees, but 85. Let's pretend it's 90. So the 10 omega O will level with the 90 degrees right here. This is kind of the crude placement of angle at a frequency equal to 10 times of the cutoff frequency or the break frequency. But we know it is not 90, it's actually 85. So it's 5 degrees under. Then after that, what happens? Obviously, if you go to 100 times of omega O, this angle will approach asymptotically towards the 90 degrees. So what is the profile? The profile will be like this. 0 degrees, it will go straight line. Lines will be, the dots, the points will be collinear. Then going horizontal. So this will be the approximation. Straight line approximation. Okay, these are kind of, marker lines. If you wish to correct it, if you wish to refine it, you need to take care of that by adjusting for the corners. So if you want to pass a curve, kind of a smooth curve, you know that the real point will be 4 degrees under, about 4.8 degrees under, 4.8 degrees over that point. And then truly it passes through this point. That's an accurate, exact point. So fit a curve. It will be asymptotic here. It will pass through here, pass through the center, pass through here, and it will asymptotically approach towards that. So The blue one that I drew against a three-piece linear approximation will be the refinement of that function, refined version of the function. So in this fashion, we can construct the zero Bode plot of a transfer function that possesses a zero. Okay. So in here, I only went all the way to case 4, but there are other versions. Now, it gets a little bit more complicated when you tend to have a complex pole. Because in a complex pole, you have two poles, of course. When that happens, the situation gets a little bit complex, which at the end of the example, I suggested that for case 5 and the 6, go and check the book, but I will tell you what it does. I will not even give you an example on that one. It's going to be reviewed again, I know, in your next course. But if you happen to have a complex pole, it does have a normalized form of its own. Which I will refer you to your book. Here. Case 5, complex poles. First of all, if your transfer function had a denominator, a second order denominator, with two real poles, you could break up those two real poles into two single ones, like two separate ones. That's easy. Then you could apply the same rules as we did for single poles for each one. And then you could look at the whole thing as a product. But in the complex poles, it will be impossible to break them up to two real poles. You will have complex. Generally, the function will look like h of s equal to omega o squared, s squared plus 2 zeta omega o s plus omega o squared. We had a zeta in the beginning of the differential equation. Zeta is called damping factor. If zeta happens to be less than 0.7, we're going to get a special behavior out of it. Generally, when it comes to that, your m of omega, which we need to calculate, will become a function of zeta and a function of omega. So this is the general shape. Okay, that will be the general shape. You will see a maximum on the top of the transfer function. M of omega will have a maximum there. So I will just look at the equation here for the second order. Let me see if I can locate and write it. There you are. Okay. The omega peak the book is calling it omega peak, will depend upon the omega O through the equation omega O multiplied by square root of 1 minus 2 zeta squared. So depending what the value of the zeta is, omega O is multiplying that, and that will be sort of a resonant frequency. The system will have a maximum gain at that point. So if you're putting a sine wave in, your gain is the highest at that point. So it will enhance that amplitude. If you pass that point, past this frequency, the resonant frequency, it will start decreasing. It will go towards the negative dB. So this can be computed from the transfer function itself. Usually the transfer function comes in terms of numbers, but you have to normalize them into that form. It's easy, pretty much. Simply factor out the coefficient there, then match what stays here against omega O squared, match that one again to zeta omega O. Then you can work it out. How much is the omega O? How much is zeta? Generally, the resonant frequency will be there. And if zeta happens to be a small number, low damping in the system, the square will be a small number, and the peak frequency will be very close to this last frequency, omega O times that. If zeta is 0, it will be exactly equal to omega O. See here. If you have no damping in the system, zeta 0, it means you have two complex poles placed like on the j omega axis here. One pole will be j omega O, the other one will be minus j omega O, and that is when zeta is equal to 0. Once zeta is like somewhat positive, maybe half, the poles will move here. Then you have a damping situation. Actually, it is possible to show that this angle, alpha, cosine of alpha is the damping. Cosine of alpha formed in the origin with respect to the complex pole is the damping factor of that circle. So when alpha becomes 90 degrees, cosine of 90 is a 0, so it takes the poles right over there. So poles migrate there. The difference is the poles in here will oscillate forever. The impulse response will be oscillatory, but the impulse response here will decay, will die down, will decay. So it is related. Really, if a system is underdamped, it will show in the frequency response domain. You will see a peaking when you're applying a sinusoidal test input. Okay, the next thing is book is calculating is an omega z. Omega z is this corner. These are all reference to your book. It is equal to radical 2 times omega peak. Okay, so once you spot that point, your resonant frequency, radical 2 times of that, which is like 40% more, will spot the zero crossing of frequency response curve. So here it will be a 0 dB. It means gain will be 1, because gain is 1 in here. Magnitude of h of j omega is 1. That's why log of 1 is a 0. 0 times 20 is a 0. So it will mark this point. Not bad, because we have this corner of the function. We know that it is going to be asymptotic here. We have that frequency. The next thing is locating this maximum It's called M peak. M peak is also related to the damping. Okay, let me try to find. I'm looking actually for my glasses, but I think I left somewhere else. So let me try to figure it out where it would be. There it is, okay. The M peak will be equal to minus 10 log of 4 zeta squared minus 4 zeta to the 4. Okay. This will determine the peak position of the peak and its frequency. And what happens after this point, way past the resonant frequency? Way past that point, we're going to have an asymptotic curve which will be from omega O. Omega O is here. It will be actually here. Omega O. With a slope of minus 40 dB per decade. So the slope of that line, which eventually becomes an asymptote, unlike the single pole, it will be at a double rate, minus 40 dB per decade, spotted from the omega O. So you can initially, once you figure out omega O, find it, and from that point, draw a line with a slope of minus 40 dB. How do you do that? It's very easy. Get omega O, get 10 times of omega O. Go find where is minus 40 here, spot the point, then draw the line. Now, how do you sketch the curve? Simply you have to fit it through asymptotically coming here, rising to that peak point. You have the coordinate. You have the coordinate here, and you know that it's going to be asymptotic to that line. So this will be the projection of both plot in a complex with a complex pulse. I didn't give you any handout on that, kind of try to summarize because the book has already done that work for you. Simply read that part section of the book, it will tell you. Also the phase angle. The phase angle will be here. It will be from the 0 degrees. Here, 0 degrees going towards the minus 180 degrees, 90 degrees, approximately. The curves will be here, a little short of, yeah, they will pass all of them through. And they will become asymptotic to the 180 degrees. And as zeta gets smaller, the decline at that point towards the 90 degrees will be even sharper. So here, zeta is increasing this way, increasing in that direction. So if zeta is 0, it will be almost like abrupt, quite abrupt. It will be almost like a step in the phase change for 0. As it is increasing, the curve will be kind of transition of the phase angle will be much, much smoother. So this is the general phase behavior, which is, I know, it's more involved, a little bit more complex, but that is how a complex pole is going to behave. Again, it is difficult to come up with linear approximation to that, but it's always possible to do that. You have to see what the curve is. You have to create some kind of a straight line approximation to that and incorporate that with the other poles and zeros. I admit it is a much harder exercise. Now, let us go over the example that I gave with a very simple real poles. So let me just erase the board and put the focus on the example. Incidentally, what will be the case of complex zeros? It will be exactly same characteristic, except it will be flipped backward. So it will go like this, go down, and then go up. Exactly if you flip this picture upward, the two complex zeros are going to behave that way. The phase angle, instead of lagging, it will be going like this, leading to a maximum of 180 degrees. We won't go that far. It's just for you to know. As I said, this is just an introduction to both at this level, because you have just done your AC. You are just out of phasors. You maybe just absorbed the concept of phasor analysis and then Laplace transformation and all of that. And this is just the first introduction to the boat. So let's start simple, but you will be introduced to that over and over again throughout the several courses. Filter design, control engineering, it's like, what, whole year of continuation. Now, let's take a look at the example. Example 1, I will give you just one example. It says sketch the Bode plot of h of s equal to s plus 100 over 10 times s plus 10. So this system has, number 1, j omega and sigma. This system has a pole at -10. It has a 0 at -100. That's the pole and a 0. Generally, once you have a transfer function and you see multiple poles and multiple zeros, it means if you have multiple poles and multiple zeros, it means more complex transfer function. If you have multiple poles, the pole that is the nearest to the origin is referred to as the dominant pole, because most of the response, that will be the slowest decaying natural frequency within the system. Here, for example, you've got e to the minus 10t. So if this was a located at the -100, it would be e to the power -100t. So for t equal to 0.1 second, this is e to the -1, but this is e to the -10. So this is completely dead, decay. That decays, but much slower. So the one that decays much slower is called the dominant pole. It's by the distance. So remember, closer is the pole, that's the dominant pole. If the zero was closer than the pole, so the transfer function would be dominated by the zero. So the closest one is always the dominant one. Either it's pole or it's zero. Okay, so we have a transfer function. We wish to get the complete overall response. This is the case of a program. So convert h of s into two simple transfer functions, standard. You get s plus 100 over 100 multiplied by 10 over s plus 10. So if you look at it, both of them are normalized function. It just happened to be that way with the numbers that I gave you. If not, if this wasn't 10 by accident, was something else, you have to create it. So if this was, say, 1, induce 100 in the denominator, post 100 at the top, induce a 10 in there, post a 10, so it will be 10 times of the whole thing. So you would have a gain. Log of 10 is 20, so all of the graph that you create would shift up by 10 decibels, just moving the picture upward, translating vertically for a constant that is other than 1. So this is 1 times of the standard, 1 times of the total standard. Now, in order to create the function, here is how we're going to get it. So h of j omega is j omega plus 100 over 100 times 10 over j omega plus 10. I call that T1. I call this T2, transfer function number 2, and we are literally multiplying it. So how do we get to the overall? If I plot 20 log of T1 separately, and I plot 20 log of T2 separately, and I add 20 log of T1 to 20 log of T2, I will create 20 log of T1 times T2. So this is T1 times T2. T1 of S times T2 of S. Well, that's the whole purpose of logarithmic scale. 20 log, 20 log. So how do we create the logarithmic? So here is how to do it. I chose a scale for you. I chose a wide scale. I went from 0.01, then 0.1s of the radian, 1s of the radian, 10s of radian. Then we go to the hundreds, the Ks, 1 Ks, 10 Ks, and even hundreds of thousands if necessary, but we won't go that far. So this will be our dB scale. dB scale. Let's do the gain first. Utilizing our standards. So remember what I said. Let us start with the pole, T2. That. Let's graph it systematically. I look at that, identify your omega O. Your omega O is 10, so go mark it. This is your omega O of 1, let's call it. Omega O of 1. That's the cutoff frequency pertaining to the pole of transfer function T2. All right. Now we know how their poles are going to look like. They're going to be horizontal, and then they're going to slope down. Now, horizontal, constructed all the way to here. the sloping. How do I create a slope? Check the scale. This is minus 20, minus 40 dB, etc., etc. And this is positive 20, positive 40 decibel. Okay, so I want to draw a line animating from here with a slope of going down 20 dB or falling 20 dB for every tenfold increase in the corner frequency. My corner frequency happily happened to be at 10. So 10 times of that is going to be 100. So go to the 100. Go to the 100 and mark it against the 20. Against the 20. So for a decade, tenfold increase, we are going to drop 20 dB. Mark this point. Draw the linear approximation. There you are. What you have here is the 20 log of transfer function 2. And the slope is equal to minus 20 dB per decade. We got that. That's the slope. So this is out of the way. Step 4. Next, let us create T1. So we are focusing on this chunk here. It's a 0 because S is in the numerator. Location of the 0 is at 100. Go find it. This is the omega O of let's call it, you know what? I'm going to call this omega O of P for pole. P for pole. Let's go find omega O of the Z. So that's the mark. Next, go find 10 times of that pole. So 10 times of the 100 will be here. Go up 20 dB. Here, mark that point. So decade, 1000 is 10 times of the 100. 1 decade increase in the frequency is causing 20 dB increase in the gain. So construct the slope. This slope is now positive 20 dB per decade. Then mark this 0. We are done almost. Now we have to compose the whole transfer function. Composing the transfer function is addition of the two lines. You have to gain some skill in doing that. Let me see if I have a better marker. No, do I not? Okay, so this will be our combination of the two graphs. Wish I can get a blue one. I think this will work. Okay, so keep adding the functions together. You have two functions. One is P2, the other one is 20 log of T1. It's this one. So if you add them, then the result will be 20 log of T1 plus 20 log of T2. That will be equal to 20 log of T1, T2, the product, because they are multiplying here. See, they are multiplying. So addition. It's 0 from here all the way. Both functions have a 0 value. So the full function will be 0 all the way to here. In the interval 10 to 100, the brown one, the top one, is still 0. the lower one is going down with that function. So the resultant will be equal to this. Combination of the two, addition of the two lines. From this point onward, here's the trick, how you will do it. Begin from this point. If you see a slope is going down -20, so it is adding increments of -20 dB per every decade. This one is adding increments of +20 dB per decade. So the net rate is going to be 0. Therefore, the line is going to be horizontal from this point onwards. So the blue one is indeed what you have here is 20 log of T1 multiplied by T2, the magnitudes. And by definition, this is the whole classical function. So we got the blue one as the both plot of this complex function when presented as a J omega. So you see why it is so convenient to deal with the lines. That's why it is so popular. You just construct the straight line approximation for zeros, 2 lines, or poles, again, 2 lines. And if it is a pole in the origin, it will be just a sloped line all the time, no breakpoint. If it is a 0, it will be slope up, pole slope down, no breakpoint. And you simply keep adding the lines together until you form the final solution. Now, if it comes to the correction and you wish to kind of refine it, what would you do? Refinement. Please note, for the poles, the red one, there was only a 3 dB down. So if you walk 3 dB under the 0 to -3 dB, mark this point. We know that the actual curve goes asymptotic to that, then passes through here. In these corners, you should do 3 dB adjustment to the top because zeros, the adjustment was upwards. So it will be 3 dB higher than that one. Therefore, the refined curve has got to be something like this, going through here, then through there, then becoming asymptotic. If you need to shape them or kind of, smooth them out, that's the way to do it. But always be aware of the corners. If it is looking down, it's from a pole, so it has to go 3 dB down. If it is looking up, it must be from a 0, so it has to go 3 dB higher. So that point should be actually -17 above the 20 by 3 dB. So that is called the correction. Now, the phase angle. Let's see how the phase angle is going to look like. Let me see the space. Okay. So I need to take away from the board a little bit. In here. So I can draw the phase angle. The phase angle is going to be okay. Same scales, 0.1, 0.01s, 0.01s, 0.1s, 1s, 10s, 100s, 1Ks, and here about 10Ks. Okay. So, and the axis, you have 45 degrees, 90 degrees. That says 0 degrees. Remember, this was a 0.01. And that is a -45. minus 90 degrees. Now we need to construct the phase angles. Okay, here's how to do that. For the transfer function, the pole, let's start with T2, the pole. For the pole, you need to find your breakpoint, omega O pole, which is at 10. Here, exactly here. We know that pole is creating 45 degrees back. So you will mark that point here. We know that at 1/10 of the pole, the phase angle is negligible, like 5 degrees. So it's like 0 degrees. So we mark this one. For a frequency 10 times over the natural frequency omega O pole, it's going to be almost like 90 degrees. So it's going to be right here. Now, this is the graph of angle of T1. Angle of T1. You construct that, okay? You will construct it. Next, let's take a look at the angle of T2, which is the 0, this guy. This is the behavior. We know that at the break frequency, 100 here, they lead by 45 degrees. That's for the 0, because at 100, omega equal to 100, the angle of the top is at 45 degrees. So you mark. At a frequency much less than 100, say a tenth of the 100, which is 10, the angle of the top is almost like 0. So you will mark that. At a frequency 10 times over the 100,000, it's almost like a 90 degrees lead. So it will bring you right there. These 3 points will be automatically collinear. So you will construct them. From that point onwards, it will stay leading 90 degrees. Under the 10, it will be 0 degrees phase shift. So what you have up there is the angle of T2. Let me see, T1. Sorry. This is the T1 actually, I'm sorry. This guy is the T2. I want to stay consistent. This is the T2. Combination. And the final step. How do we combine the lines together? Okay. Now we need to add these 2 lines together. Okay, here's how you will add. In the interval from lowest frequency all the way to 1, it's going to stay 0 because blue and the red, they have 0 band. From 1 all the way to 10, this interval, notice the blue one is a 0, but the red one is going down. So the sum of the 2 functions will go down all the way to here. From this point onward, notice please that all the way to 100, check this portion and that one. Whatever the blue one is adding, the red one at the same rate is taking away. So the response is going to stay horizontal. That's the tricky part you have to observe. Now we are here. At this point, notice the red one is not adding, doesn't have any rate, but the blue one has a rate. So you should draw a line parallel with that blue one, which will exactly take you to that point. Once you reach this point, now none of them have any rate, any slope. So it's going to be horizontal. The brown curve that you see is the profile of the phase angle of the 2. It is actually minus 10 to the minus 1 of omega over 10 minus tan to the minus 1 of, actually 1 is a positive, this one, yeah, plus tan to the minus 1 of omega over 100. This is the theta tot. It's that function. Function comprised of two inverse tan function. It's the brown one. So how does it look like? In real term, the smooth function of phase angle should be going from here about 5 degrees under that bend. It will reach here and it will bend about 5 degrees over that and will be 5 degrees under that asymptotically. So we know, we have an idea. The combination of these two functions, if you're applying a sinusoidal wave, it's going to give you a phase lag. So output is going to lag the input. But I know that lag angle is never going to exceed more than 45 degrees. Look, the information I gathered about the phase angle. This is called the phase lag circuit. Phase lag circuit. Phase lag circuits happen when the pole dominates over the zero. It's close. Had I chosen 0 in here, a pole here, this picture that you see would be exactly inverted. So instead of going like that down, it would go up, ramp up, and then stay steady. It would flip this picture upward, and it would flip the phase angle upward. And I would be getting a phase lead, So the output would be leading. I can even estimate where it would be. Where is the maximum of that lead? Somewhere between these two numbers, 100 and the 10, somewhere there. That will be the minimum point or maximum phase shift. Similarly, same way I can calculate for the maximum positive phase lead. This circuit is called the phase lag. Not very popular, but this one is a phase lead, and it is an extremely important element, phase lead network, for the control engineering, like 1 year down the line, where you will stabilize the system by managing its phase angle, making correction to its phase angle, which is a problem and a cause for instability in the system. So it is a really deep knowledge, deep skill applied to the control engineering. And today I showed you how the gain and the phase angle can be constructed for a bigger transfer function, like utilizing 2 stages of the transfer function. Okay, so this is all I could do for today. So next week we will come together this time, and I will give you a little review of what we did and give you an idea what to study for the final examination. This will not be in the final examination. So I can give you, you can feel at rest. This is not going to be in the final examination. It's a last topic. Your examination will be emphasized on the Laplace transforms, 2 questions on the Laplace transforms, 1 question on the AC power, 1 question on AC phasor analysis, kind of evenly distributed over the most important topics of this course. Okay. Have a nice weekend, and I'll see you later. Take care.